Neptune looks peaceful from a distance. From Earth, from anywhere in the inner solar system, it appears as a faint blue point of light. Calm, still, a distant, serene world at the edge of the solar system, barely distinguishable from the stars around it without a telescope. This is perhaps the most misleading first impression of any planet we know. Neptune is not peaceful. It is not calm. It is not distant in the sense of being safely irrelevant. It is the most violently dynamic atmosphere in the solar system. It contains winds faster than anything measurable on any other planet. It harbours storms larger than Earth that have persisted for decades. Its moon, Triton, is moving toward it in an inward death spiral that will end in either a catastrophic collision or the formation of a ring system larger than Saturn's. Its magnetic field is so bizarre and tilted that no straightforward model of planetary interiors can fully account for it. And we have visited it exactly once. One spacecraft, one flyby, 12 hours of close approach. Voyager 2 in August 1989. That is the entirety of humanity's direct observational data on the most distant known planet in our solar system. Everything else we know about Neptune comes from Earth-based telescopes, increasingly powerful ones, supplemented by that single brief encounter over 3 decades ago. Everything we think we know about Neptune has this caveat built in. We barely know it at all. Tonight we're going to follow what we do know and what we do not know honestly, precisely, and without minimizing the things that make Neptune genuinely strange and genuinely dangerous by any meaningful definition. Not dangerous in the sense of threatening Earth directly, but dangerous in the sense that it represents an environment so extreme, so far beyond anything in human experience, that it defies description in ordinary terms. If you have this on because the night is long, stay. Neptune's story is one of the most underappreciated in planetary science. The planet we know least about may be the strangest one we have. Let us start with the basics. Neptune is the 8th and most distant planet from the Sun in our solar system. Its average distance from the Sun is approximately 30.1 astronomical units, about 4.5 billion kilometers. Light from the Sun takes roughly 8 minutes to reach Earth. It takes approximately 4 hours and 10 minutes to reach Neptune. The signal from Voyager 2, when it made its closest approach, travelling at the speed of light, took 4 hours to reach Earth. Neptune's diameter is approximately 49,500 kilometers, about 3.9 times the diameter of Earth. Its mass is approximately 17 times Earth's mass. Despite being smaller in diameter than Uranus, Neptune is more massive, a fact that already hints at something unusual about its interior composition. Neptune is classified as an ice giant, distinct from the gas giants Jupiter and Saturn, which are composed primarily of hydrogen and helium. Neptune and Uranus both contain large amounts of water, methane, and ammonia in their interiors, not as ices in the everyday sense, but as hot, compressed fluids under enormous pressure. The word ice in this context is somewhat misleading. These materials are at temperatures of thousands of degrees Celsius in Neptune's interior. They are called ices because of their chemical composition, not their physical state. Neptune has 14 known moons. The most significant is Triton, an extraordinarily unusual object we will discuss in detail. It also has 6 known rings, faint, incomplete ring arcs rather than the full rings of Saturn, discovered by Voyager 2. Neptune has an orbital period of approximately 165 years. It completed its first full orbit since discovery, which occurred in 1846, in 2011. We have observed it for less than one complete orbit. No human civilization has watched Neptune go all the way around the Sun since humans have been watching the sky carefully enough to see it. Now let us talk about why Neptune is not peaceful. The winds. Neptune has the fastest winds of any planet in the solar system. Not the fastest in absolute terms, the winds of some exoplanets are much faster, but faster than any other planet in our solar system, and faster by a margin that should be impossible given how little energy Neptune receives from the Sun. At the cloud tops, Neptune's winds reach speeds of approximately 2,100 kilometers per hour, about 580 meters per second. This is well above the speed of sound at Earth's surface. These are not gusts, these are sustained wind speeds. The fastest wind speeds ever recorded on Earth during the most extreme tropical cyclones at the edges of tornado vortices barely reach 400 kilometers per hour. Neptune's ambient wind speeds are 5 times faster. For comparison, Uranus, Neptune's twin in size and composition, has winds of roughly 250 kilometers per hour. Jupiter's famous Great Red Spot has internal wind speeds of about 130 kilometers per hour at the eye wall. Saturn has winds of up to about 500 kilometers per hour at the equator. Neptune, 2,100 kilometers per hour. Sustained, planet-wide. Why? This is one of the genuinely puzzling aspects of Neptune's atmosphere. Neptune receives about 900 times less solar energy per unit area than Earth. It is so far from the Sun that sunlight there is a dim glow rather than the intense illumination we know. You might expect a cold, quiet atmosphere with gentle winds driven by what little solar energy arrives. The opposite is true. The leading explanation is that Neptune generates significant internal heat. Neptune emits approximately 2.6 times more energy than it receives from the Sun. Something inside Neptune is generating heat. The exact mechanism is debated, but it likely involves ongoing gravitational settling or release of energy from formation still slowly radiating outward, billions of years later. This internal heat drives convection in Neptune's atmosphere more powerfully than solar heating alone would. But this explanation, while plausible, does not fully account for the specific pattern of Neptune's winds. Why are the fastest winds at the equator pointing westward, opposite to the planet's rotation, while the polar winds point eastward? Why is the wind structure so organized into bands rather than chaotic convection? These questions do not have fully satisfying answers. Neptune's atmosphere does things we cannot fully explain using the physics we understand. This is unsettling, not because it suggests danger to us directly, but because it means that a planet we can barely see from Earth, that we have visited once, briefly, is behaving in ways that challenge our models of atmospheric dynamics. Let us talk about the storms. Neptune's most famous atmospheric feature is the Great Dark Spot, a massive anticyclonic storm system observed by Voyager 2 in 1989. It was roughly the size of Earth. Its internal winds, measured at the edges of the system, were among the fastest ever recorded on any planet, approaching 2,400 kilometers per hour at the eye wall. Then the Great Dark Spot disappeared. When the Hubble Space Telescope turned to Neptune in 1994, it was gone. In its place at the North Pole was a new dark spot forming. By 1995, that spot also appeared to be dissipating. This is extraordinary. Jupiter's Great Red Spot has persisted for at least 350 years, possibly much longer. It is shrinking, but slowly. Neptune's great storms appear and disappear on timescales of years. The current understanding is that Neptune's dark spots are high-pressure systems in the upper atmosphere, anticyclones, that form and dissipate relatively quickly by comparison with Jovian storm systems. The exact mechanism for their formation and dissolution is not fully understood. New dark spots have been observed since 1989 by Hubble. A particularly notable one appeared in 2018 and was observed changing over subsequent years. For the first time, astronomers were able to observe in detail the behavior of a dark spot forming, developing, and beginning to decay. What they found was unexpected. The storm did not decay in the expected way, moving toward the equator and dissipating there as models predicted. Instead, it produced a separate, smaller, bright cloud feature that appeared to split off from it. The dynamics were more complex than the models anticipated. Every time we look at Neptune more carefully, it surprises us.
Let us talk about the atmospheric composition and what it means for the conditions inside. Neptune's upper atmosphere is approximately 80% hydrogen and 19% helium, similar to Jupiter and Saturn. But these are the trace outer layers. Beneath this relatively thin outer envelope, the composition changes dramatically. The interior of Neptune is thought to consist of a hot, dense fluid of water, methane, and ammonia under extreme pressure, the icy mantle that gives ice giants their name. This region occupies most of Neptune's volume. Pressures in the deep interior likely reach millions to billions of atmospheres. Temperatures in the deep interior may reach 5,000 to 7,000 degrees Celsius or higher. Under these conditions, water does not behave like water. Methane does not behave like methane. At extreme pressures, matter enters exotic states that we can only partially recreate in laboratory experiments. One hypothesis, experimentally supported in recent years, is that deep in Neptune's interior, extreme temperature and pressure conditions cause methane to break down into carbon and hydrogen. The carbon, under enormous pressure, forms crystals, diamond crystals, which then sink because diamond is denser than the surrounding fluid, in what theorists have called a diamond rain. This is not a wild speculation. Laboratory experiments using powerful lasers to briefly recreate the pressure and temperature conditions of Neptune's interior have produced diamond precipitation. The conditions where this would occur in Neptune are real. Whether the process actually occurs at the scale required and produces the effects theorized is still debated, but the experimental evidence for the underlying physics is real. Inside Neptune, it may be raining diamonds, continuously, for billions of years. The diamonds would sink toward a core, a rocky, possibly metallic core, roughly the size of Earth, at Neptune's center. They would accumulate. There may be a vast ocean of liquid diamond deep in Neptune's interior, with solid diamond chunks floating in it like icebergs. Let us now talk about Triton, because Triton might be the most unusual moon in the solar system, and its existence is one of the most direct indications that Neptune's past was far more violent than its current appearance suggests. Triton is approximately 2,700 kilometers in diameter, slightly smaller than Earth's moon. It orbits Neptune at a distance of about 354,800 kilometers. These basic facts sound unremarkable. What is remarkable is Triton's orbit. Every other large moon in the solar system orbits its planet in the same direction as the planet rotates, what astronomers call prograde motion. This is what you expect. When planets form, they acquire moons from the same disk of material rotating in the same direction. It is a basic consequence of angular momentum conservation. Triton orbits Neptune retrograde, in the opposite direction of Neptune's rotation. This can mean only one thing. Triton did not form alongside Neptune. It was captured. Triton is a wandering Kuiper belt object, similar in composition and origin to Pluto,
that strayed too close to Neptune and was gravitationally captured into orbit. This capture event was catastrophic for the early Neptunian system. The gravitational interaction that captured Triton would have destabilized any original moons Neptune had formed with. Neptune's original moon system was very likely destroyed in the process, the original moons either ejected into the outer solar system or plunging into Neptune itself.
What we see as Neptune's moon system today is essentially rebuilt from scratch after Triton's capture. A handful of small inner moons that condensed from the debris of the collision, and Triton itself, the interloper. Triton is also inexorably, irreversibly spiraling inward. Because Triton orbits retrograde, tidal forces between Triton and Neptune are decelerating Triton rather than accelerating it. When a moon orbits in the same direction as its planet rotates, and the planet's rotation is faster than the moon's orbital motion, tidal forces transfer energy to the moon, pushing it outward. This is why Earth's moon is slowly receding. When a moon orbits retrograde, tidal interactions drain energy from the moon's orbit, pulling it inward. In approximately 3.6 billion years, give or take, Triton will cross the Roche limit. The Roche limit is the distance from a planet inside which the planet's tidal forces are stronger than the gravity holding a moon together. Inside the Roche limit, a moon is torn apart. When Triton crosses the Roche limit, it will be torn apart. Its material will spread into a ring around Neptune. The resulting ring system would be denser than Saturn's current rings and would span an enormous area around Neptune. This is already happening, slowly. Triton is currently about 11 times the Roche limit from Neptune. In geological terms, this seems comfortable, but on astronomical timescales, it is a death sentence already written. Triton is already doomed, already falling, already on an inescapable inward trajectory that will end in its destruction. Neptune currently orbits the Sun roughly where it is because of a long, violent, dynamical history. The solar system is not the orderly, stable place it may appear from the inner solar system. Let us talk about that history, about what Neptune's current position and Triton's captured orbit tell us about the early solar system, because this is one of the most dramatic stories in planetary science, and it fundamentally changes how we understand the stability of the solar system we live in. The current model for the early dynamical evolution of the solar system, called the Nice model, after the city in France where it was developed, proposes that the outer solar system was dramatically restructured approximately 700 million to 1 billion years after the solar system's formation. In this model, the 4 giant planets formed in a more compact configuration than they currently occupy. Jupiter and Saturn were closer together. Uranus and Neptune were both much closer to the Sun. Neptune in particular may have been closer than Uranus is today, and significantly closer than its current position at 30 astronomical units. Beyond the outer planets was a vast disk of icy planetesimals, the primordial Kuiper belt, containing perhaps 20 to 50 Earth masses of material. Then, something triggered a gravitational instability. Jupiter and Saturn crossed a resonance, a configuration where their orbital periods became related by a simple ratio, causing their mutual gravitational interactions to amplify. This triggered a cascade. Saturn began migrating outward. As it did, it scattered smaller bodies onto new orbits. Those bodies interacted with Uranus and Neptune. The ice giants migrated outward dramatically. Neptune was essentially ejected outward through the primordial Kuiper belt, scattering most of its material in the process. The Kuiper belt was once much denser. Neptune carved through it and depleted it enormously. The scattered material went everywhere,
some inward into the inner solar system, some ejected to the outer Oort cloud, some into the current scattered disk. This period of dynamical chaos in the outer solar system corresponds to what is known as the Late Heavy Bombardment, a period approximately 3.9 billion years ago during which the Moon, Mercury, Mars and Earth were heavily cratered by an intense flux of impacting bodies. This timing corresponds to what the Nice model predicts for the destabilization. During this migration, Neptune reached its current position, and Triton, which was orbiting the Sun independently as a large Kuiper Belt object at the time, was captured into retrograde orbit around Neptune in the chaos. This history is relevant for several reasons. First, it means Neptune is not in its original position. It is a migrated planet that moved outward by many astronomical units over a period of tens of millions of years, disrupting everything in its path. Second, it means the current outer solar system, the Kuiper Belt, the scattered disk, the Oort cloud, is a remnant of a far more populated early structure. Neptune sculpted the outer solar system into what we see today. Third, it means the inner solar system, including Earth, was subjected to an intense bombardment driven by Neptune's outward migration. The craters on the Moon are largely a record of this bombardment. The Earth received the same impacts. Whatever life might have been developing on early Earth was subjected to this intense cratering period. Neptune's history is our history in a very real sense. The conditions that allowed life to develop on Earth were shaped in part by the dynamical events that placed Neptune where it is. Let us now talk about Triton more carefully, about what Voyager 2 found there, because the surface and activity of Triton are genuinely among the most surprising discoveries of the Voyager program. When Voyager 2 flew past Triton in August 1989, it imaged a surface that no one had anticipated. The southern polar region was covered in nitrogen ice and methane ice, forming a pink-tinged cap. The surface was relatively young, resurfaced by geological activity, with relatively few craters compared to what you would expect on an ancient, geologically dead body. And the surface was erupting. Voyager 2 detected active geysers on Triton. Not volcanic geysers. Triton has no liquid water near the surface. These were nitrogen geysers. The surface temperature of Triton is approximately minus 235 degrees Celsius, about 38 Kelvin above absolute zero. It is one of the coldest measured surfaces in the solar system. At this temperature, sunlight, even the dim sunlight that reaches Neptune, is enough to warm dark subsurface material slightly. The dark material absorbs solar radiation and heats the nitrogen ice above it. The nitrogen vaporizes and the vapor pressure builds until it erupts through the overlying ice, shooting nitrogen gas and dark dust particles up to 8 kilometers above the surface. Dark streaks were observed on Triton's surface, trails of dark material deposited by these geysers, blown downwind across the ice plains. Active geological processes on a body this cold, this far from the Sun. It means that even at minus 235 degrees Celsius, with solar input nearly 1,000 times weaker than at Earth, there is enough energy to drive complex surface processes. Triton's surface also shows a characteristic terrain called cantaloupe terrain, a complex surface texture resembling the skin of a cantaloupe, thought to have been formed by diaporism, the upwelling of denser material through less dense material in a gravitational instability. This is a geological process seen on Earth and on other worlds, but occurring here in frozen nitrogen and methane rather than silicates.
The internal structure of Triton is thought to include a rocky core, possibly a liquid water ocean maintained by tidal heating from Neptune, and an icy mantle and crust. The tidal heating that is slowly spiraling Triton inward is also potentially keeping its interior warm enough to maintain a liquid ocean. Triton may be another subsurface ocean world in addition to Europa, Enceladus, Ganymede and others. But Triton's ocean, if it exists, is on a timer. In 3.6 billion years, the Moon will be torn apart. Its ocean, if it has one, will be scattered across Neptune's ring system. Let us now talk about Neptune's magnetic field, because it is one of the most unusual and poorly understood magnetic fields of any planet we have examined. Earth's magnetic field is generated by convection in the liquid iron outer core, a process called a geodynamo. The field is roughly aligned with Earth's rotation axis, tilted by about 11 degrees. Jupiter's field is also roughly aligned with its rotation axis. Saturn's is almost perfectly aligned, the most symmetric planetary magnetic field known, aligned to within 1 degree. Neptune's magnetic field is tilted approximately 47 degrees from Neptune's rotation axis, and its center is offset from the planet's center by about 0.55 of Neptune's radius, more than halfway from the center to the surface in one direction. This means Neptune's magnetic field is not generated at the center of the planet.
It appears to be generated in the outer layers, possibly in the ionic ocean of hot pressurized water-ammonia fluid, where ions can move and carry current. If the magnetic field is generated in the outer icy mantle rather than in a deep metallic core, the dynamics of that generation process would be very different from what we understand about Earth's geodynamo. Uranus has a similarly bizarre magnetic field, tilted about 59 degrees, offset by about 0.3 planetary radii. Two planets with similarly unusual magnetic fields suggest this is not a coincidence. Something about the structure of ice giants produces these offset, tilted magnetic fields. We do not have a fully satisfying physical model for why. One consequence of Neptune's tilted and offset magnetic field is that the magnetosphere, the region of space dominated by the planet's magnetic field, tumbles wildly as Neptune rotates. Unlike Earth's relatively stable magnetosphere, Neptune's magnetosphere oscillates dramatically as the planet turns. The geometry of the field at any point in space near Neptune changes enormously over a single rotation period of about 16 hours. This has implications for the radiation environment near Neptune. The behavior of charged particles trapped in the magnetic field is more complex and less predictable than around planets with more symmetrical fields. We do not fully understand this, and Triton, orbiting within this complex, tumbling magnetosphere on a retrograde orbit, experiences a radiation environment that is unlike anything else in the solar system. Let us now talk about what Neptune's moons tell us more broadly. Beyond Triton, Neptune has 13 other known moons, though they are much smaller. The largest of the inner moons is Proteus, roughly 420 kilometers across, with a heavily cratered irregular surface. Hippocamp, discovered in 2013 from Hubble images, is one of the smallest moons known. It orbits Neptune very close to the ring system and appears to be a fragment of the outer moon Proteus, possibly knocked off by an ancient impact. These small inner moons orbit Neptune within the ring system in a complex, potentially unstable configuration. Because Triton's retrograde orbit causes ongoing tidal evolution, the gravitational environment for these inner moons is slowly changing. Over very long timescales, the stability of their orbits cannot be guaranteed.
Neptune's ring system itself is notable for being incomplete, featuring distinct arcs rather than continuous rings. The arcs were first observed from Earth and confirmed by Voyager 2. They are named Liberty, Equality and Fraternity, reflecting the French origin Nice model terminology that has become standard. Why are there arcs rather than complete rings? In an unperturbed system, ring material should spread azimuthally and form a complete ring relatively quickly. The maintenance of arcs over long timescales requires some mechanism to confine material in certain regions. The current model invokes gravitational resonances with the moon Galatea, a moon orbiting just interior to the main ring system, which creates a resonance pattern that confines material. But the confinement is imperfect, and the arcs are not stable indefinitely. Observations over several decades show the arcs changing. They may be dissipating. Neptune's rings may be a transient feature, material that was disturbed from some previous configuration and is slowly spreading. Like Triton's inward spiral and the uncertain stability of the inner moons, it suggests a system that is dynamically evolving, not a static, peaceful arrangement. Let us now talk about what we do not know about Neptune, which is a surprisingly large amount. We have one flyby's worth of data, 12 hours of close approach in 1989 with Voyager 2's instruments. Everything since then has been telescopic observation from Earth or from near-Earth space. We do not know the precise structure of Neptune's interior, the presence and size of a rocky core, the exact nature of the icy mantle, the depth at which various phase transitions occur, the degree of differentiation. These are inferred from mass, radius, and magnetic field measurements, but not directly observed. We do not know whether diamond precipitation actually occurs. The laboratory experiments support the physics. Whether it occurs at the required scale in a real planetary interior is an inference. We do not know the source of Neptune's internal heat with certainty. The excess heat emission is measured. The cause is debated. We do not fully understand Neptune's magnetic field generation mechanism. We have observations of its geometry. We do not have a complete physical model. We do not know the detailed atmospheric dynamics. The wind speeds we have come primarily from the Voyager 2 flyby and subsequent Hubble and ground-based tracking of cloud features. The three-dimensional structure of the atmosphere, how winds change with altitude, what drives specific weather systems, is poorly constrained. We do not know the composition and structure of the deep interior adequately. The icy mantle description is a model category, not a detailed characterization. The exact proportions of water, methane and ammonia, their state at various depths, the ionic and electrical properties, these are estimated, not measured directly. We do not know whether Triton has a subsurface ocean. It is plausible given its tidal heating and composition, but has not been confirmed. We do not know the surface composition of Triton in detail. Voyager 2 observed only the southern hemisphere in any detail during its brief flyby. The northern hemisphere was largely unobserved. We do not know the current state of Neptune's atmospheric dynamics. The last detailed imaging was Voyager 2 in 1989. Hubble has provided remarkable images since then, but limited spectroscopy and no in situ measurements. This list of unknowns is not a list of minor details. It includes some of the most fundamental physical questions about the planet. We know Neptune less thoroughly than we know many objects that are billions of light years away. Let us now talk about what a mission to Neptune would look like, and why one has not been sent since Voyager 2. The distance is the fundamental challenge.
Neptune, at its closest approach to Earth, is still approximately 4.3 billion kilometers away. The communication delay, the time for a signal traveling at the speed of light, is approximately 4 hours each way. A spacecraft requires sophisticated autonomy to operate, given that ground controllers cannot respond to problems in real time.
Voyager 2 reached Neptune after 12 years of travel, using a trajectory that took it past Jupiter, Saturn, and Uranus using gravitational assists. This type of planetary alignment, allowing this efficient trajectory, occurs rarely. The specific alignment used by Voyager 2 occurs approximately every 175 years. More direct trajectories to Neptune are possible using Jupiter gravity assists, but still require approximately 12 years minimum travel time. This is a long mission, requiring instruments and systems that can operate reliably for over a decade in the deep space environment. Despite several proposed missions, Argo, which would have been a Voyager-like flyby, Neptune Odyssey, a proposed orbiter and atmospheric probe, none has been approved and funded for flight. NASA's 2023 to 2032 Planetary Science Decadal Survey, which sets priorities for planetary missions for the next decade, ranked a Uranus orbiter and probe as the top flagship mission priority for the 2020s. Neptune received lower priority in part because of the trajectory. The Jupiter gravity assist opportunity, optimal for a Neptune orbiter, departs in the late 2020s and early 2030s. If no mission is launched in that window, the wait for the next comparable opportunity is approximately a decade. If a Neptune mission were launched in the late 2020s using a Jupiter gravity assist, it would arrive at Neptune in the late 2030s or early 2040s, nearly 50 years after Voyager 2. What would such a mission reveal? Likely things we cannot fully anticipate. The history of planetary exploration is full of cases where the first close observation of a body revealed things completely unexpected. Triton's geysers were unexpected. Neptune's wind speeds were unexpected. The ring arcs were unexpected. A Neptune orbiter would be in a position to observe the atmosphere continuously over years rather than hours, to track the evolution of storm systems, to characterize the magnetic field in 3 dimensions, to observe Triton's geysers, map its surface, measure its internal heat, and potentially confirm or deny the presence of a subsurface ocean, to measure the composition of the ring arcs and determine their stability, to search for additional small moons. The scientific return would be enormous. And yet, the mission has not been funded. We remain, for now, limited to our telescopes and our 30-year-old data. Let us now talk about what the atmosphere of Neptune would actually feel like if you were somehow transported there, as a way of making the extreme conditions concrete rather than abstract. If you were positioned in the upper cloud layer of Neptune, at the altitude where the atmospheric pressure is approximately equal to Earth's surface pressure, 1 bar, the temperature would be approximately minus 210 degrees Celsius. The sky around you would be dark. Neptune receives about 1/900th of Earth's solar illumination at the top of the atmosphere, and much less penetrates to the cloud level. The colour of the atmosphere, the blue that makes Neptune visually distinctive, comes from methane absorbing red wavelengths of sunlight. But with so little sunlight at this depth, you would see only dim blue-grey murk. The wind would be catastrophic by any human standard. At 2,100 km per hour sustained. There is no equivalent experience on Earth. The fastest winds in a tornado peak briefly at perhaps 500 km per hour. Neptune's winds are more than 4 times stronger and sustained globally rather than confined to small regions. These winds carry not clean air, but mixtures of hydrogen, helium, methane, ammonia, and water vapor
at temperatures far below any biological survival threshold.
Any exposed biological material would simultaneously freeze and be subjected to mechanical forces far beyond structural tolerance. Below the 1 bar level, the pressure increases rapidly. At 10 bars, the temperature is still around -170 degrees Celsius. At 100 bars, it has risen to approximately 100 degrees Celsius. At this depth, the atmosphere is dense enough that it begins to transition toward what we might call the interior fluid. No clear boundary between atmosphere and deeper interior, just a continuous thickening. At pressures in the megabar range, millions of atmospheres, the temperature reaches thousands of degrees. Water becomes a conducting ionic fluid. Methane, under these conditions, dissociates. The carbon atoms are under sufficient pressure to adopt a diamond structure. Going deeper still, toward the center, pressures and temperatures increase further. The rocky core at the center, if the model is correct, is under pressures of many millions of atmospheres and temperatures of thousands of degrees Celsius. Neptune has no surface to land on. There is no clear boundary between an atmosphere and a solid or liquid surface. You would simply be compressed and heated as you sank into an increasingly dense, hot fluid until you were destroyed, at pressures and temperatures far beyond anything we can create in most laboratory conditions. Let us now talk about what makes Neptune scientifically significant beyond its intrinsic strangeness, about why understanding Neptune matters for understanding planets generally. Ice giants are the most common type of giant planet found in other star systems. Surveys of exoplanets have found that planets in the size range of Neptune and Uranus, sometimes called sub-Neptunes, are among the most common types of planets orbiting other stars. More common than gas giants like Jupiter. More common than rocky super-Earths. Our solar system has 2 ice giants. The exoplanet census suggests most planetary systems have even more planets in this size range. We understand gas giants relatively well. Jupiter and Saturn have been visited by orbital spacecraft that observed them for years. We understand rocky planets reasonably well. Earth is one, and we have visited Mars, Venus, and Mercury multiple times. Ice giants are the poorly understood middle category that may be the most common. Understanding Neptune and Uranus is therefore not just about understanding 2 specific planets. It is about understanding a class of planets that may be the dominant form of planet in the galaxy. The internal structure of ice giants, the nature of the ionic ocean, the mechanism of their unusual magnetic fields, the source of their excess heat, the behavior of matter at these intermediate pressures and temperatures, is relevant to interpreting every exoplanet observation of a sub-Neptune. When we observe an exoplanet transiting its star and measure its radius and mass and infer its density and perhaps its atmospheric composition, our interpretation of what that planet is like internally depends on models. Those models must be calibrated against objects we can actually study in detail. Neptune is one of only 2 ice giants accessible for detailed study. Every uncertainty in our knowledge of Neptune propagates into every exoplanet interpretation involving ice giant-sized worlds. Let us now talk about something more specific, about how Neptune was discovered, because the story of its discovery is one of the most remarkable in the history of science, and also reveals something important about how much the outer solar system can surprise us. By the 1840s, Uranus had been observed for decades. Its orbit could be calculated with great precision using Newton's laws. But the observed positions of Uranus did not quite match the predictions. The planet was not where it should be. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, working independently, realized that the discrepancy could be explained by the gravitational pull of an undiscovered planet. They calculated where this planet should be. On the evening of September 23, 1846, astronomer Johann Galle at the Berlin Observatory turned his telescope to the position Le Verrier had predicted and found Neptune within 1 degree of the predicted position, essentially exactly where the math said it should be. This was considered one of the greatest triumphs of Newtonian mechanics. A planet discovered by pure calculation, found precisely where theory predicted. What followed was less celebrated. Further observations of Neptune's orbit over subsequent decades showed that Neptune itself had small discrepancies from its predicted orbit. This led to the search for a 9th planet, Planet X, which eventually led to the discovery of Pluto in 1930. But Pluto is too small to account for the orbital discrepancies. The discrepancies turned out to be measurement errors. There is no 9th planet definitively required by Neptune's orbit. But the story is instructive. Neptune was discovered because of orbital discrepancies. Pluto was searched for because of apparent orbital discrepancies. There are ongoing searches for a hypothetical Planet 9, a large planet in the outer solar system proposed to explain the clustering of orbits of certain trans-Neptunian objects. If Planet 9 exists, a significant if, it would be another massive body in the outer solar system that we have not directly observed. The outer solar system may hold significant surprises still. Neptune itself, when found, was immediately strange. Le Verrier had predicted it would appear as a disk rather than a point of light in moderate telescopes, confirming it was a planet rather than a star. And it appeared exactly as predicted. But Triton was discovered just 17 days after Neptune itself, by William Lassell, an English astronomer. Its retrograde orbit was recognized as unusual from early observations. Within weeks of discovering the planet, observers had already found one of its strangest features, the moon that should not be where it is, orbiting in the wrong direction. Neptune announced itself as strange from the moment of its discovery, and has maintained that character ever since. Let us now talk about seasonal changes on Neptune, another aspect that demonstrates how little we actually know about this world. Neptune's axial tilt is approximately 28.3 degrees, similar to Earth's 23.5 degrees. This means Neptune has seasons. But Neptune's orbital period is 165 Earth years. Each Neptunian season lasts approximately 40 years. Since Neptune was discovered in 1846, humanity has observed less than one complete orbit and approximately one complete seasonal cycle. We are just now reaching the point where we have watched Neptune go through a complete set of seasons. What does a Neptunian season actually look like? The limited observations we have suggest that Neptune's atmosphere changes significantly with season. The brightness of the southern hemisphere has increased since Voyager 2's visit in 1989, consistent with warming as the southern hemisphere has moved towards summer. The activity of cloud features appears to be correlated with the seasonal cycle, but we have only been watching carefully for a few decades with instruments capable of tracking these changes. We do not have a complete picture of how Neptune's seasons unfold, how its weather systems evolve over a full seasonal cycle, or how the atmosphere responds to the slow change in solar heating angle. The 40-year seasonal timescale is longer than the careers of most scientists. Understanding Neptunian seasons requires observations extending across human generations of observers. This is an underappreciated aspect of the outer solar system. The timescales on which it operates are simply longer than human institutions typically plan for. A full characterization of Neptune's climate would require sustained observational effort over centuries. Let us now talk about the specific way Neptune fits into the broader story of the solar system's history. About Neptune not just as a planet, but as an agent that shaped the solar system we live in. Beyond the Nice model's description of Neptune's outward migration, Neptune continues to shape the outer solar system today through its gravitational influence. The Kuiper belt, the vast region of icy bodies beyond Neptune's orbit, extending from about 30 to 50 astronomical units, is structured by Neptune's gravity. Neptune is in resonance with many Kuiper belt objects. Pluto, for example, is in a 3:2 mean motion resonance with Neptune. Pluto completes exactly 2 orbits for every 3 Neptune orbits. This resonance was not an accident. It is a consequence of Neptune's outward migration. As Neptune moved outward, it swept up KBOs into these resonances, a process called resonance sweeping. The objects in 3:2 resonance with Neptune, called Plutinos because Pluto is the most famous of them, are literally the remnants of Neptune's migration history. The outer edge of the classical Kuiper belt, which drops off sharply at about 48 astronomical units, is another signature of Neptune. This edge marks roughly where Neptune's gravitational influence was strongest during its migration. Beyond Neptune's direct resonance influence is the scattered disk, a population of objects on highly elliptical orbits extending out to hundreds of astronomical units. These were scattered by gravitational encounters with Neptune during its migration. They are the survivors of a violent process. Further still, at tens of thousands of astronomical units, is the Oort cloud, a vast spherical halo of comets. The Oort cloud contains comets that were scattered from the inner solar system early in its history, gravitationally pushed outward by interactions with the giant planets, including Neptune. The comets that occasionally appear in Earth's inner solar system, falling inward from the Oort cloud after being perturbed by passing stars or galactic tides, have trajectories that were originally set by interactions with Neptune and the other giant planets billions of years ago. Neptune is not just a distant, irrelevant world, it is the gravitational gatekeeper of the outer solar system. Its position, its mass, and its historical migration define the structure of everything beyond it. Let us talk about something that rarely comes up in discussions of Neptune, about the specific experience of darkness at that distance from the Sun, and what it means for understanding Neptune as a place. At Neptune's distance from the Sun, 30.1 astronomical units, the inverse square law of light intensity means that sunlight is approximately 900 times weaker than at Earth. The Sun, viewed from Neptune, would appear as an intensely bright point of light, far brighter than any star, still brilliant enough to cause eye damage if looked at directly, but providing roughly the same illumination as a slightly overcast day on Earth. Not pitch dark, but deeply dim by the standards of the inner solar system. The implication is that Neptune receives very little solar energy. Earth receives approximately 1,361 watts per square meter at its distance from the Sun, the solar constant. Neptune receives approximately 1.5 watts per square meter, about the amount of energy from a dim nightlight spread over an entire square meter. This is why the wind speeds are so puzzling. With only 1.5 watts per square meter of solar input, there should be very little energy available to drive atmospheric dynamics.
The winds on a planet receiving this little solar energy should be gentle. They are not gentle. Neptune's internal heat source, that 2.6 to 1 ratio of emitted to received energy, is the resolution. Neptune is generating more energy internally than it receives externally. But why? Uranus, Neptune's compositionally similar twin, does not show significant internal heat emission. Uranus emits roughly as much energy as it receives. Its ratio is approximately 1.06, essentially in equilibrium. This is the mystery that Uranus and Neptune jointly pose to planetary scientists. Two similarly sized, similarly composed ice giants, formed in similar regions of the early solar system, evolved very differently in terms of their internal heat. One leading hypothesis focuses on the difference in their impact histories. Neptune may have formed normally, emitting heat from gravitational contraction that has been slowly radiating away for 4.5 billion years.
Uranus may have been struck by a large object during the solar system's early history, an impactor that knocked it to its extreme axial tilt of 98 degrees, which is so tilted that Uranus essentially rolls around the Sun on its side, and that this giant impact disrupted Uranus's internal convection, creating some kind of lid that prevents heat from escaping efficiently. If this is correct, Uranus is abnormally cold, not radiating as much heat as it should, and Neptune is more typical of ice giants. The heat Neptune emits is primordial heat from formation and gravitational settling, still slowly leaking out. But we do not know. We do not have enough data on either planet to definitively answer this question. The difference in internal heat between Uranus and Neptune, two planets that should be nearly twins, is one of the most significant unresolved puzzles in comparative planetology.
And it matters because it tells us about the formation and impact history of the outer solar system, and because it affects how we interpret the interiors and atmospheres of ice giant exoplanets. Let us now talk about what Voyager 2 actually experienced during those 12 hours at Neptune, about the mission itself, because the circumstances of that encounter were extraordinary. Voyager 2 was launched in August 1977. It performed flybys of Jupiter in 1979, Saturn in 1981, and Uranus in 1986. By the time it reached Neptune in 1989, it had been travelling for 12 years. Its instruments were designed for the inner solar system conditions of the 1970s and had been operating in the cold, radiation-saturated environment of the outer solar system for over a decade. The navigation required for the Neptune encounter was extraordinarily precise. Voyager 2's trajectory was adjusted to fly past Neptune at a specific distance and angle that would both provide close observations of Neptune and send it on a course to fly past Triton. The gravitational field of Neptune would then slingshot the spacecraft into a trajectory heading southward out of the ecliptic plane. This required hitting a targeting box, the region of space Voyager 2 needed to pass through with extraordinary precision after 12 years and billions of kilometers of travel. Engineers had been making small trajectory corrections throughout the journey. The targeting was successful. At closest approach on August 25, 1989, Voyager 2 passed within approximately 4,800 kilometers of Neptune's cloud tops, closer than any previous planetary flyby by Voyager. The spacecraft had only hours to gather data before Neptune receded behind it. Every observation had to be scheduled precisely in advance because the communication delay, 4 hours each way, made real-time adjustments impossible. The spacecraft then continued to Triton, passing within approximately 40,000 kilometers of the Moon 5 hours after closest approach to Neptune. And then it was gone. The encounter
was over. The data was transmitted back to Earth, and no spacecraft has returned since. The team that processed Voyager 2's Neptune data, the scientists and engineers who worked through the data returned from that encounter, produced a scientific understanding of Neptune that we are still building on more than 30 years later. Some of them have watched their entire careers pass while waiting for a follow-up mission that has not yet been approved. There is something almost poignant about this. A civilization capable of sending a spacecraft 12 years to Neptune, achieving a successful flyby and returning extraordinary data, and then not going back. Not because it is impossible, because of priorities and funding and the simple difficulty of planning projects that span decades. Neptune remains, after all this time, one of the least known places in our solar system, a world we glimpsed once and have been studying from a distance ever since. Let us now talk about the specific observations Voyager 2 made at Neptune that were most surprising, the things that differentiated Neptune from what scientists had predicted. Before Voyager 2, scientists expected Neptune to be broadly similar to Uranus, dim, cold, largely featureless by comparison with Jupiter and Saturn. The models suggested a planet in equilibrium with its solar input, with relatively subdued atmospheric dynamics. The first surprise was the Great Dark Spot. Nothing in the pre-encounter models predicted a storm system of that magnitude and wind speed. The storm's internal winds, approaching 2,400 kilometers per hour, were faster than the highest predicted wind speeds for Neptune's atmosphere. The second surprise was Triton. While Triton's retrograde orbit had been known from Earth-based observation, its surface was expected to be ancient and heavily cratered, a dead world preserved in cold storage. Instead, it was geologically active, with young terrain and active nitrogen geysers. No one predicted geysers on a body at minus 235 degrees Celsius. The third surprise was the magnetic field. Models had anticipated a magnetic field broadly similar to those of the other giant planets, roughly aligned with the rotation axis generated by a core dynamo. The actual field, tilted 47 degrees, offset enormously from the planet's center, required completely new thinking about how ice giant magnetic fields are generated. The fourth surprise was Neptune's rings, not their existence, which was suspected from Earth-based stellar occultation observations, but their structure. The distinct arcs were more organized and more complex than expected, and the mechanisms required to maintain them imposed new constraints on the dynamics of the ring system. The fifth surprise, perhaps the most profound, was simply how active Neptune was. Its atmosphere was dynamic, complex, and full of features at a level that its very low solar input should not support. The planet was doing far more than its position in the solar system seemed to allow. Every one of these surprises reflects the same underlying truth. We did not understand Neptune well enough from a distance to predict what we would find up close. And we still do not understand it well enough. The models have improved, the questions are sharper. But Neptune continues to exceed our theoretical expectations. Let us talk now about the question of habitability, about whether any part of the Neptunian system could conceivably support life as we understand it. The direct answer is almost certainly not in Neptune's atmosphere or on its surface, because there is no surface. The conditions throughout Neptune's atmosphere and interior are hostile to any chemistry that produces biological molecules as we understand them. The temperatures are either far too cold in the upper atmosphere or far too hot in the deep interior. The pressures in the deep interior are far too high. The chemical environment includes highly reactive species. There is no liquid water at any accessible location. Triton, however, is a more interesting case, not because it is likely habitable, but because it illustrates the concept of habitability in extreme environments. Triton has a composition that includes organic molecules. Voyager 2 detected complex organic compounds on its surface from the interaction of radiation with methane and nitrogen ices. The same radiation environment that produces these organics also destroys complex molecules, but over long timescales there is a steady-state production of organic chemistry. If Triton has a subsurface liquid water ocean maintained by tidal heating, that ocean would be in contact with a rocky sea floor. The combination of liquid water, rocky minerals, chemical gradients from hydrothermal activity, and organic molecules is precisely the set of conditions that some researchers believe supported the origin of life on early Earth. Triton's ocean, if it exists, ticks several of those boxes. But there is a significant complication specific to Triton: its finite future. In 3.6 billion years, Triton will be destroyed. If its ocean could support life, that life would have a fixed expiration date, not determined by stellar evolution, not by environmental catastrophe in the conventional sense, but by the fundamental dynamics of the Moon's orbit. Any life in Triton's ocean would be living inside an object that is already on an inescapable trajectory toward destruction. The question is whether life, if it arose in that ocean, could do anything about that fact. The answer, almost certainly, is no. It would simply experience its world until the tidal forces that maintained the internal heat also, eventually, tore its world apart. There is something philosophically striking about this scenario. A world potentially capable of supporting life, but with a destruction date set from the moment the Moon was captured into its retrograde orbit, perhaps 4 billion years ago. Let us now talk about the specific scientific instruments that future missions to Neptune would need to carry, and what they could tell us that we do not currently know. An orbiter, a spacecraft that enters orbit around Neptune rather than simply flying past, would be transformative. The difference between a flyby and an orbiter is the difference between a photograph and a years-long documentary. An atmospheric probe, a separate vehicle released into Neptune's atmosphere to descend until pressure and temperature destroy it, transmitting data the whole way, would directly measure the composition, temperature profile, wind speeds, and chemical abundances at various depths. This is how we confirmed the deep structure of Jupiter's atmosphere with the Galileo probe in 1995. A Neptune atmospheric probe would tell us the deuterium to hydrogen ratio in the deep atmosphere, a diagnostic of where Neptune formed in the early solar system. It would directly measure wind speeds and directions at multiple altitudes. It would measure the abundance of noble gases, xenon, krypton, argon, which serve as tracers of planetary formation conditions. It would measure the ratio of carbon, nitrogen, oxygen, key constraints on interior models. An orbiter would allow systematic mapping of Neptune's magnetic field geometry over multiple orbital passes, enabling construction of a three-dimensional model of the field rather than the single snapshot Voyager 2 provided. An orbiter with radar instruments could potentially probe the interior structure of Triton, detecting internal layering, including a possible ocean. An orbiter would allow tracking of weather systems over years, watching the development and decay of dark spots, monitoring the seasonal evolution of cloud patterns, observing how the atmosphere responds to the slow change in solar input over the 40-year season. If a small atmospheric probe were deployed at Triton, a lander or cryobot, it could directly sample the surface ices, measure the composition of the geyser plumes, and search for organic molecules. If subsurface access were possible, it could search for biosignatures in the hypothetical ocean, though this is well beyond near-term capabilities. These are not fantasies. Every instrument type mentioned has been built and flown or is in development. The question is not technological capability, but political will and funding. A Neptune system orbiter with an atmospheric probe and a Triton surface element would be one of the most scientifically return-rich missions in planetary science. It would address fundamental questions about planetary formation, the behavior of matter at extreme conditions, the origin of unusual magnetic fields, the dynamics of icy moon systems, and potentially the habitability of subsurface oceans. It has not been approved. Let us now talk about Neptune in the context of the search for life elsewhere, about how Neptune and Triton fit into the broader landscape of where we are looking and why. The search for life in the solar system has expanded dramatically over the past 30 years. The discovery of subsurface oceans on Europa, Enceladus, Ganymede, and possibly Titan, revealed through spacecraft data, transformed our understanding of where in the solar system liquid water might exist. Liquid water is considered the most important single prerequisite for life as we know it. The key insight is that liquid water does not require proximity to the sun. Internal heat sources, radioactive decay, tidal heating, can maintain liquid water far from the solar habitable zone. Enceladus is at 9.5 astronomical units from the Sun, yet its subsurface ocean is warm enough to support hydrothermal systems that were directly sampled by Cassini through the Moon's geyser plumes.
Triton, at 30 astronomical units, pushes this concept to its limit. It is heated by tidal forces from Neptune. If those tidal forces are sufficient, a question that depends on the detailed mechanical properties of Triton's interior, a liquid water ocean could exist beneath the ice. If Triton has an ocean, it extends the potential habitable zone of our solar system to 30 astronomical units. And by extension, the concept of a habitable zone defined by stellar proximity becomes largely irrelevant for subsurface ocean worlds. What matters is whether tidal or radiogenic heat can maintain liquid water, not where the star is. This has implications for the search for life beyond the solar system. Ice giant moons at large orbital distances around other stars could harbour liquid water oceans. They would be invisible to current telescope observations, too small and too cold to detect directly. But they might exist in enormous numbers throughout the galaxy.
Triton is the nearest example of an object that might be such a world. Understanding it better, confirming or denying its ocean, understanding its tidal heating budget, characterizing its chemistry, would directly inform our understanding of how common such worlds might be. And all of this depends on getting a mission to Neptune. Let us now talk about the specific challenge of communicating with a spacecraft at Neptune's distance, because this is one of the concrete engineering obstacles that makes Neptune exploration so different from Mars exploration or even Jupiter exploration. The speed of light is 299,792 kilometers per second. At Neptune's average distance of 4.5 billion kilometers, the one-way light travel time is approximately 15,000 seconds, about 4 hours and 10 minutes. A round-trip communication, a question sent, an answer received, takes approximately 8 hours and 20 minutes minimum.
This is qualitatively different from operating a Mars rover, where the communication delay is between 3 and 22 minutes. In that range, ground controllers can still have a responsive relationship with the spacecraft. Problems can be identified and responses formulated within a reasonable operational timescale. At Neptune, real-time control is simply impossible. A spacecraft orbiting Neptune must be largely autonomous. It must be able to detect problems, diagnose them, and respond to them without waiting for instructions from Earth. If a fault occurs that threatens the spacecraft must handle it itself. This is achievable. Voyager 2 operated autonomously throughout its journey, but it requires sophisticated fault protection software and robust hardware. The spacecraft must be designed to survive without ground intervention for periods measured in days to weeks. The communication bandwidth is also limited by distance. The radio signal strength falls off with the square of distance. At Neptune's distance, even with the largest ground antennas available, the 70-meter dishes of NASA's Deep Space Network, the data rate achievable is extremely low. Voyager 2 transmitted data at rates measured in kilobits per second. A future Neptune orbiter would use more sophisticated radio systems and potentially optical laser communication to achieve higher rates. But the fundamental challenge of distance remains. The data volume returned from a Neptune mission will be limited by physics. Every image, every spectrum, every measurement must compete for transmission time on a low bandwidth link that is 4 light hours long. Mission designers must make careful choices about what to measure and transmit and what to process on board. These constraints shape what kind of science is possible. High-resolution video imaging, easy for a spacecraft in Earth orbit, is extremely challenging for a Neptune orbiter.
Wide-area surveys of Triton's surface to search for features of interest would need to be done at lower resolution to fit within the available data budget. Prioritization of scientific measurements becomes more critical the farther you go. These are solvable engineering problems, but they illustrate why Neptune exploration is genuinely hard, not just in the poetic sense of being far away, but in the concrete engineering sense of every system having to work without support for years in an environment that provides essentially no feedback to ground controllers in real time. Let us now talk about what the atmosphere of Neptune looks like from above, from the perspective of a spacecraft approaching it, because the images Voyager 2 returned and the subsequent Hubble images have revealed a visual character to Neptune that is both beautiful and strange. Neptune's colour, its characteristic deep blue, is due to methane in the upper atmosphere. Methane absorbs red and infrared wavelengths of light preferentially. When sunlight enters Neptune's atmosphere, the red wavelengths are absorbed by methane, and the blue wavelengths are reflected back. The result is the striking deep azure colour visible in images. Uranus has similar methane in its atmosphere, but appears much paler, more of a blue-green. The reason for this difference in colour, despite similar composition, is not fully understood. One hypothesis is that a higher altitude haze on Uranus scatters light before it can reach the methane absorption layer, diluting the blue colour. Another hypothesis involves differences in atmospheric dynamics affecting the distribution and particle sizes of aerosols. The visual appearance of Neptune's cloud tops reveals the planet's violent dynamics. The bright clouds, composed of methane ice crystals condensing in the upper atmosphere, are not subtle. They form rapidly, evolve, and move visibly even in images taken hours apart. Voyager 2 images showed cloud features bright enough to cast shadows on the cloud layer below, a phenomenon called cloud shadow casting that had previously only been observed on Earth and Venus among planets. The dark storms, the Great Dark Spot and its successors, appear as darker regions where deeper, warmer atmospheric layers are visible
through gaps in the upper cloud cover. Their interaction with the surrounding cloud field produces complex, swirling patterns, visible in moderate detail. The overall visual impression of Neptune is of an active, turbulent world. Nothing about its appearance suggests the deep quietude that its remoteness and dim solar illumination might imply. It looks dynamic because it is dynamic. In recent years, Hubble observations have tracked new storm systems forming in Neptune's northern hemisphere, now approaching summer as the seasons shift from the southern summer observed by Voyager 2 to the northern summer expected in the 2040s.
The northern hemisphere cloud activity has increased, consistent with the seasonal warming pattern. Dark spots have appeared and changed on timescales of years. Neptune is not a static world. It changes, and we are watching it change, slowly, from a great distance, with limited instruments, without the close-up capability needed to understand what we are seeing. This is the situation we are in with Neptune, a world that is genuinely extreme in its conditions, a world that shapes the outer solar system, a world that holds a moon, Triton, on a trajectory toward destruction that it cannot escape, a world whose magnetic field we cannot fully explain, a world whose interior produces phenomena, possibly including diamond rain, that we can only partially recreate in laboratory conditions. A world that may be the closest example in our solar system of the most common type of planet in the galaxy. And a world we have visited once, 35 years ago, for 12 hours. Let us talk about the specific numbers involved in Neptune's winds, because the numbers themselves, examined carefully, reveal just how far outside ordinary experience Neptune's atmosphere actually is. The fastest wind speeds ever recorded on Earth occurred inside a tornado near Bridge Creek, Oklahoma in 1999, measured by Doppler radar at approximately 512 kilometers per hour. This is considered exceptional, a brief, localized, rare extreme of terrestrial atmospheric dynamics. Most of Earth's severe weather operates at wind speeds well below this. Neptune's sustained global wind speeds at cloud top level, approximately 2,100 kilometers per hour. This is more than 4 times the fastest tornado ever measured on Earth. But the crucial difference is the word sustained and the phrase global. The Bridge Creek tornado was a narrow funnel a few hundred meters wide, lasting less than an hour. Neptune's 2,100 kilometers per hour winds are not a localized extreme. They are the background state of the planet's atmosphere at certain latitudes. They encircle the entire planet. They have been observed across decades of observation. They are not a storm event. They are normal. At 2,100 kilometers per hour, the wind is moving at 583 meters per second. The speed of sound in air at Earth's surface is approximately 343 meters per second. Neptune's winds are travelling at nearly 1.7 times the speed of sound at Earth's surface. They are supersonic relative to Earth's atmosphere. In Neptune's own atmosphere, the speed of sound is different. It depends on the composition, temperature and pressure of the local gas. Hydrogen-helium atmospheres at Neptune's temperature have a speed of sound somewhat higher than Earth's, roughly 1,000 to 1,200 meters per second at cloud-top temperatures. So Neptune's winds, while fast, are not necessarily supersonic within Neptune's own atmospheric reference frame. But they are fast by any absolute standard. And these winds are not uniform. The westward equatorial jet, the fastest winds, blowing opposite to Neptune's rotation, coexists with polar eastward jets at higher latitudes. The transition between these regimes involves complex shear zones, where winds at adjacent latitudes are moving in opposite directions at hundreds of kilometers per hour difference. In such shear zones, Kelvin-Helmholtz instabilities can form, the same instabilities that create the characteristic wave patterns visible when clouds move at different speeds at different altitudes in Earth's atmosphere. On Neptune, these instabilities occur at planetary scale, producing turbulent mixing zones that affect weather pattern formation and the evolution of storm systems. The vertical wind shear, the change in wind speed and direction with altitude in Neptune's atmosphere, is also substantial. Observations of discrete cloud features at different altitudes show different drift rates, implying that the atmosphere is not moving as a rigid block, but has significant variation in wind speed across different altitudes. All of this is inferred from tracking visible cloud features in images. We have no direct measurement of wind profiles at different altitudes. That would require an atmospheric probe. The Galileo probe at Jupiter directly measured wind speeds at multiple altitudes as it descended, revealing dramatic vertical structure that could not be inferred from cloud tracking alone. For Neptune, we have only the cloud tracking. The actual vertical structure of Neptune's winds is largely unknown. Let us talk about the Great Dark Spot's disappearance in more detail, because it illustrates something important about Neptune's atmosphere that distinguishes it from Jupiter. Jupiter's Great Red Spot has existed for at least 350 years. Historical records suggest it may have been observed as far back as the 1660s. Over this time, it has changed. It was once much larger, roughly 3 times Earth's diameter, and has shrunk to slightly larger than Earth's diameter in recent decades. But it has persisted as a coherent structure. Why does Jupiter's storm persist for centuries, while Neptune's storms last only years? The difference likely lies in the nature of what drives the storms. Jupiter's Great Red Spot is an anticyclonic storm, maintained by the difference in wind speed between the jet streams above and below it. These jet streams are, in turn, maintained by deep convection and the planet's rapid rotation. Jupiter's jet streams are extremely stable. They have been observed to maintain essentially the same positions and speeds for decades. The stable jet streams provide a stable boundary condition for the storm to sit in. Neptune's jet streams, while fast, appear to be less stable in position and speed. The storms that form in them therefore have less stable boundary conditions to maintain themselves against. They dissipate when the jet structure that supports them changes. This instability may reflect the different nature of what drives the atmospheric dynamics. Jupiter's jets are driven primarily by rotation and internal convection from the deep hydrogen atmosphere. Neptune's jets involve the complex dynamics of a highly variable internal heat source acting on a compositionally different atmosphere with a different relationship to solar forcing. The fact that Neptune's storms form and dissipate on human timescales, years rather than centuries, is actually an observational advantage in one sense. We can watch a complete storm life cycle. We can observe a dark spot from formation through maturity to dissipation. We did this with a dark spot observed by Hubble in 2018 to 2020, watching it develop and begin to break down. What we found was unexpected behavior during the dissipation phase. The parent storm developed a bright companion cloud that appeared to split off and persist even as the dark spot itself faded. This behavior had not been predicted by any of the leading models of Neptune storm dynamics. The models had to be revised. Neptune keeps revising our models. Every time we look more carefully, the atmosphere does something slightly different from what we anticipated. Let us talk about the specific composition of Triton and what it tells us about the Kuiper belt. Because Triton is our best studied large Kuiper belt object, even though it is now in orbit around Neptune rather than orbiting the Sun independently. Triton's surface is composed of frozen nitrogen, with smaller amounts of methane ice, carbon dioxide ice, carbon monoxide ice, and more complex organic compounds produced by radiation processing of the simpler ices over billions of years. This composition is similar to what has been measured on Pluto and other large Kuiper belt objects from Earth-based spectroscopy. This similarity is the key evidence that Triton originated in the Kuiper belt rather than forming alongside Neptune. Triton's composition is characteristic of cold, outer solar system bodies that formed at large distances from the Sun, where temperatures allowed these volatile ices to condense. Pluto, which has been studied in detail by the New Horizons mission in 2015, provides an independent comparison point. Pluto's surface composition is remarkably similar to Triton's, as measured by Voyager 2 in 1989. Nitrogen ice dominant, methane ice present, complex organics tinting the surface reddish-brown. The similarity suggests that large Kuiper belt objects formed in a compositionally consistent environment, and that Triton, despite its capture into Neptune orbit, retains the chemical character of its original Kuiper belt environment. But Triton's composition has been modified by its time in Neptune orbit. The tidal heating that maintains its internal temperature also drives geological activity that resurfaces parts of the Moon, potentially erasing the original chemical signature in resurfaced regions. The radiation environment in Neptune's magnetosphere is also different from the deep Kuiper belt environment where Triton spent most of its early history. Triton is therefore a complicated object to interpret. It is a Kuiper belt object modified by billions of years in a very different environment. Disentangling the original Kuiper belt signature from the Neptune system modifications requires data we do not currently have. Comparing Triton to Pluto in detail, using the New Horizons data on Pluto's composition, geology, and atmospheric structure, allows us to ask specific questions about what Triton's time in Neptune orbit has done to it. If we see differences between Triton and Pluto in specific chemical signatures or geological features, some of those differences may reflect the different environments they have occupied. This comparative approach, using New Horizons Pluto data alongside the Voyager 2 Triton data, has been productive for researchers. But it is limited by the fact that the Triton data is 35 years old, low resolution by modern standards, and covers only the southern hemisphere in any detail. A dedicated Triton mission, whether a flyby or an orbiter, would transform this comparison. Modern instruments would characterize Triton's surface composition at resolutions comparable to New Horizons Pluto data, allowing quantitative comparison of the two worlds that would constrain models of Kuiper belt composition and the effects of Neptune capture on Triton's evolution. Let us talk about the relationship between Neptune and the late heavy bombardment and what it means for the history of life on Earth. The late heavy bombardment is the term given to a period approximately 3.9 billion years ago, roughly 700 million years after the solar system formed, during which the inner solar system experienced an intense flux of impacting bodies. The evidence is in the crater record on the Moon, Mercury, and Mars. The Moon, in particular, shows a concentration of large impact basins that have been dated to approximately this period. Earth was also subjected to this bombardment. The Earth's geological record from this period is largely erased by plate tectonics and erosion. But zircon crystals from Australia, dated to this era, among the oldest materials on Earth, show geochemical signatures consistent with intense impact processing of the early crust. The origin of the late heavy bombardment is debated, but the Nice model, which involves Neptune's outward migration through the primordial Kuiper belt, provides a natural explanation. Neptune's migration would have destabilized the primordial Kuiper belt, scattering material into the inner solar system and producing the bombardment pulse. If this is correct, if Neptune's migration is responsible for the late heavy bombardment, then Neptune's history directly intersects with the history of life on Earth. The oldest evidence for life on Earth is from approximately 3.5 to 3.7 billion years ago. Microfossils and geochemical biosignatures from that era. The late heavy bombardment ended approximately 3.8 to 3.9 billion years ago. Life appears in the fossil record very shortly after the bombardment ended. This timing could be a coincidence, or it could mean that the late heavy bombardment, despite being an intense period of destructive impact events, was not the extinction-level catastrophe it might appear. Life may have survived the bombardment in deep environments, hydrothermal vents, deep subsurface refuges, and rebounded rapidly once the impact flux declined. Some researchers have even proposed that the bombardment could have delivered organic molecules and water to the early Earth, material from the outer solar system scattered inward by Neptune's migration. The chemistry of comets and asteroids includes the building blocks of biological molecules. If bombardment delivers these materials, it could contribute to, rather than simply threaten, the conditions for life. In this view, Neptune's migration, violent as it was, may have played a role in establishing the conditions for life on Earth. Not through any mechanism of direct delivery, but through the broader dynamical process that structured the solar system into its current form. This remains speculative. The exact mechanism and timing of the late heavy bombardment are still debated. The Nice model is not universally accepted in all its details. The connection between Neptune's migration and Earth's early biological history is indirect, but the connection exists in outline. Neptune is not unrelated to our existence. It is part of the dynamical context in which Earth's history unfolded. Let us now talk about something more immediate, about what Neptune looks like today from Earth, and what our best telescopes can currently tell us. The Hubble Space Telescope has been the primary tool for monitoring Neptune since 1990. Its views of Neptune, while not achieving the close-up resolution of Voyager 2, have been remarkable in several respects. Hubble can resolve Neptune as a disk. It can track cloud features over time, measuring their motion and thereby inferring wind speeds. It can observe in ultraviolet wavelengths inaccessible from the ground, revealing additional atmospheric structure. And crucially, it can do this repeatedly, over years and decades, providing the time baseline needed to track seasonal changes and storm evolution. Hubble's Neptune observations have revealed the appearance and disappearance of dark spots since 1994. They have documented the brightening of the southern hemisphere as the southern summer matured. They have tracked the evolution of bright cloud complexes. They have constrained the behavior of dark spots in ways that inform our theoretical models. The James Webb Space Telescope, operational since 2022, has added a remarkable new capability. Webb observes primarily in the infrared, wavelengths longer than visible light. This provides a very different view of Neptune than Hubble's visible and ultraviolet perspective. In Webb's infrared images,
Neptune's rings, faint and difficult to see in visible light, become dramatically prominent. The ring system stands out clearly in Webb data in a way that had not been achieved by any previous telescope. This reveals the ring structure in new detail and allows monitoring of ring brightness and morphology over time. Webb also sees Neptune's moons with greater clarity, particularly in the near-infrared, where the moons emit thermal radiation from their surfaces. Triton appears unusually bright in Webb's infrared images because nitrogen ice on its surface reflects the dim sunlight efficiently in these wavelengths. Very large telescope observations from the ground, using adaptive optics to correct for atmospheric blurring, have achieved spatial resolutions approaching Hubble in the visible and near-infrared, allowing detailed tracking of Neptune's cloud evolution. The combined data from Hubble, Webb, and ground-based facilities provides a multi-wavelength monitoring program for Neptune that covers from the ultraviolet through the infrared. This allows different layers of the atmosphere to be probed. Different wavelengths penetrate to different depths, building up a three-dimensional picture of atmospheric structure that no single instrument can provide alone. But all of this is still remote sensing from Earth. The resolution achievable from Earth's distance, even with the most powerful telescopes, is limited. Features smaller than roughly 1,000 kilometers across on Neptune cannot be distinguished. Individual weather systems can be tracked, but their internal structure cannot be resolved. The atmospheric depth structure is inferred from spectral models, not measured directly. The gap between what we can learn from Earth and what we could learn from an orbiting spacecraft is enormous. It is the difference between watching a thunderstorm from an aeroplane at cruising altitude and standing inside a weather balloon inside the storm. Let us now talk about the specific timing of future missions, about the trajectory mechanics that create windows of opportunity for getting to Neptune. Neptune is far. Getting there quickly requires help, gravitational assists from other planets, which redirect and accelerate the spacecraft without consuming propellant. The most useful assist comes from Jupiter, which is massive enough to provide a very large velocity boost. The trajectory geometry for a Neptune mission using a Jupiter gravity assist repeats on a timescale of roughly 10 to 12 years. The specific optimal window for a Neptune orbiter, using a Jupiter flyby to achieve the combination of travel time and arrival conditions needed for orbit insertion, was identified in several detailed trajectory studies as occurring in the late 2020s, approximately 2029 to 2034. If no mission is launched in this window, the next comparable opportunity does not occur until roughly the late 2030s or 2040s, with less favourable trajectory options in the intervening period. For a mission launched in 2029 to 2034, the travel time to Neptune using a Jupiter assist would be approximately 12 years. Arrival at Neptune would occur in the 2041 to 2046 timeframe. This timing matters for Triton science as well. Neptune's northern hemisphere, which was unobserved by Voyager 2, which visited during southern summer, will be tilted toward the Sun and entering its summer period during the 2040s. A mission arriving in the 2040s would observe the northern hemisphere during the portion of Neptune's seasons that Voyager 2 could not access. The 2040s Neptune summer in the north may reveal phenomena analogous to, but potentially different from what Voyager 2 observed in the southern summer of 1989. Triton's northern hemisphere, largely unobserved, would also be in better viewing geometry from a spacecraft in Neptune orbit during that period. From a purely scientific perspective, the 2040s are an excellent time to be at Neptune. The practical question is whether a mission can be approved, designed, built, and launched before the optimal trajectory window closes. The Neptune Odyssey concept,
a flagship orbiter and atmospheric probe proposed to the 2023 Planetary Science Decadal Survey, estimated a total mission cost of approximately $6 to $7 billion over its full development and operations period. This is comparable to the cost of the Cassini mission to Saturn or the Europa Clipper mission to Jupiter. It is expensive. It is within the range of what has been approved and funded for comparable destinations. Whether it will be approved depends on funding priorities, competition with other missions, and the political will to commit to a 12-year travel time mission whose results will not arrive until decades after the decision to fund it. Let us now talk about why Neptune, despite all of this, remains fundamentally mysterious in a way that the other planets do not. We have spent years in orbit around Mars, decades of data from multiple orbiters and landers. We know Mars in extraordinary detail: its geology, mineralogy, atmospheric dynamics, seasonal cycles, dust storm behavior, subsurface structure. We can predict Martian weather patterns. We can map the distribution of water ice across the planet's history. We have spent years in orbit around Jupiter. The Galileo mission operated for 8 years. Juno has been in orbit since 2016. We have direct atmospheric probe data. We understand the deep structure of Jupiter's magnetic field, the dynamics of its jet streams, the distribution of lightning in its atmosphere, the properties of its radiation belts. We have spent years in orbit around Saturn. Cassini operated for 13 years. We understand Saturn's ring structure in extraordinary detail, its atmospheric dynamics, the properties of its major moons, including Triton and Enceladus. We have never spent even a single day in orbit around Neptune. Everything we know about Neptune's deep interior structure, magnetic field generation mechanism, internal heat source, detailed atmospheric dynamics, ring evolution, and Triton's internal structure is inferred from 12 hours of close flyby data supplemented by Earth-based observation. For all the complexity and strangeness of Neptune that we have discussed, there is a deeper strangeness that underlies it. We do not actually know Neptune. We know a snapshot of Neptune from one brief encounter 35 years ago and a set of long-distance observations that cannot resolve the fine structure. There may be phenomena on Neptune that we have not even conceived of, surprises waiting at closer range, because our models are based on so little data that they are almost certainly wrong in important ways. Every time we have gotten close to a new planetary body, Jupiter with Galileo, Saturn with Cassini, Pluto with New Horizons, the Moon with Apollo, we have found things we did not predict. Things that required revision of theories that seemed secure. Neptune will do the same when we look closely again. We do not know what it will show us. But we know from experience that it will show us something unexpected. Let us talk about something that puts Neptune's remoteness into concrete human terms, about what it would actually mean to travel there if that were ever attempted by people rather than robots. At current propulsion technology, the fastest a human spacecraft could realistically travel to Neptune, using chemical rockets for the main propulsion with a Jupiter gravity assist, is approximately 12 years. This is the travel time Voyager 2 required, and while modern rockets are more efficient in some respects, the fundamental physics of getting to Neptune has not changed. 12 years in space, one way. The longest continuous human spaceflight on record is approximately 437 days, set by Valery Polyakov on Mir in 1994-95. The effects of that extended mission included substantial bone density loss, muscle atrophy, cardiovascular deconditioning, neurovestibular adaptation issues, and immune system changes. These were manageable. Polyakov recovered, but they required significant rehabilitation. 12 years of continuous spaceflight at zero gravity would produce physiological changes far beyond anything in the existing data. The bone loss alone, proceeding at roughly 1 to 2% per month in the spine and hips for long-duration ISS astronauts, would, if unmitigated, represent a total loss of 144 to 288% of baseline bone mineral density over 12 years. This calculation is absurd. Actual bone loss rates slow as the body adapts, but the point is that 12 years of microgravity exposure is so far beyond the existing data that we literally cannot confidently predict the outcome. Even with the best current countermeasures, resistance exercise, nutrition protocols, pharmacological interventions, we do not know whether a human could survive 12 years in deep space in a condition allowing productive work upon arrival. The radiation environment for a deep space mission to Neptune would also be extreme. Beyond Earth's magnetosphere, astronauts are exposed to galactic cosmic rays, high-energy particles from sources outside the solar system, at rates that significantly exceed NASA's current career radiation exposure limits. A 12-year mission would deliver radiation doses far beyond any exposure in the existing astronaut medical database. The psychological challenge of 12 years in a small vehicle isolated from Earth with communication delays that grow from minutes near Earth to hours as Neptune approaches would test human psychology in ways that have no analogue in any existing data. The longest previous mission involved communication with Earth at light speed, nearly instantaneous response. At Neptune, communication is impossible in real time. The crew would be genuinely on their own in a way that no human beings have ever been. These are not arguments against such a mission in principle. They are descriptions of the genuine difficulty. Future propulsion technologies, nuclear thermal, nuclear electric, solar sails driven by powerful lasers, or concepts not yet operationalized, could reduce travel times. Better life support, artificial gravity from rotating sections of the spacecraft, improved radiation shielding, and decades more experience with long-duration spaceflight could address the physiological and psychological challenges. But it is honest to acknowledge that sending humans to Neptune with any technology currently operational or in near-term development would be one of the most demanding endeavours in human history. Substantially harder than going to Mars, which itself is substantially harder than going to the Moon. Neptune makes the Moon look like the backyard. Let us talk now about what the Neptune system looks like as a whole, about how its various components interact, and what that means for understanding the system as a dynamic entity rather than a collection of static objects. Neptune sits at the centre of a complex, interacting system. Its gravity defines the orbital dynamics of all the moons and ring material. Its magnetic field, tumbling wildly as the planet rotates, creates a complex and variable radiation environment throughout the inner system. Its tidal forces act on Triton, slowly pulling it inward, generating internal heat, and driving the geological activity that makes Triton so unusual. The inner moons, Naiad, Thalassa, Despina, Galatea, Larissa, Hippocamp, Proteus, orbit within the ring system in a gravitational environment shaped by both Neptune's gravity and the perturbations from Triton's retrograde orbit. Triton's influence on the orbital dynamics of the inner moons is subtle but real, acting over long timescales to slowly destabilize some configurations. The rings, incomplete arcs maintained by resonances with Galatea, are themselves evolving. Historical observations suggest the arcs have changed in brightness and extent over the decades since Voyager 2. the arc material is being perturbed by the gravitational environment and is not in permanent stable equilibrium. On timescales of perhaps thousands to millions of years, the arcs will spread and dissipate, unless replenished by collisions between moonlets in the ring system. The whole system is slowly heading toward a future state that is qualitatively different from the present. Triton inward spiraling, rings dissipating, inner moons potentially destabilized. In 3 to 4 billion years, Triton crosses the Roche limit and is torn apart, its material spreading into a new, dense ring system that could rival Saturn's in extent. After Triton's destruction, the ring system will be dense and complex, then gradually spread and thin as collisions grind the material down and radiation pressure pushes small particles away. Over hundreds of millions of years after the initial disruption, the ring material would be depleted, leaving Neptune with only the inner small moons, themselves potentially reshuffled by the dynamical chaos of Triton's breakup. In the very long run, billions of years further, the Sun will itself evolve, eventually swelling into a red giant. At Neptune's distance, 30 astronomical units, the Sun's red giant phase will dramatically increase the solar flux at Neptune. The temperature at Neptune will rise. Ices that are currently frozen on Neptune's moons and in its rings will sublimate. The character of the outer solar system will be transformed. But on any human timescale, even geological timescales, Neptune looks essentially as it does now. The changes are happening, but slowly.
The system we see is the system that has existed in roughly this configuration for billions of years, and will continue in roughly this configuration for billions more. Except for Triton. Triton is on a timer. Geologically, that timer has hundreds of millions of years remaining before the Roche limit is crossed. On astronomical timescales, this is not distant, it is approaching. Let us now talk about the comparison between Neptune and the exoplanets that most closely resemble it, because this comparison is directly relevant to how we understand the broader population of planets in the galaxy. The Kepler Space Telescope surveyed over 150,000 stars for transiting planets from 2009 to 2018. Its successor, TESS, has extended this survey. The combined data has revealed that planets in the size range of Neptune, roughly 3 to 5 Earth radii, are among the most common type of planet orbiting Sun-like and M-dwarf stars. These planets are sometimes called warm Neptunes, or sub-Neptunes, because many of them orbit closer to their stars than Neptune does to our Sun. A warm Neptune, at half an astronomical unit from its star, would receive intense stellar radiation and have very different atmospheric conditions from Neptune in our solar system. But they are similar in bulk properties, mass, radius, bulk density, to Neptune. Understanding what is inside a sub-Neptune exoplanet, its composition, internal structure, whether it has an icy mantle or a water ocean or a hydrogen-dominated atmosphere above a rocky core, requires models. And those models must be informed by direct study of real ice giant interiors. Neptune is the ice giant we can study most directly. Its interior properties, inferred from mass, radius, gravity field measurements, magnetic field, and heat emission, provide the primary calibration point for models of sub-Neptune exoplanets. Every time a planet like Neptune is discovered orbiting another star and characterized by its radius and mass, scientists apply models that ultimately trace back to our understanding of Neptune and Uranus. The accuracy of those models, the reliability of what we conclude about these exoplanets, depends directly on how well we understand the real Neptune. If our models of Neptune's interior are wrong, if the icy mantle concept is inaccurate, if the sources and distribution of internal heat are not what we think,
then our interpretations of sub-Neptune exoplanets will also be wrong in systematic ways. There are indications that current models may indeed be incomplete. The excess heat emission we mentioned, Neptune emitting 2.6 times what it receives, is not fully accounted for by simple cooling models. The distinct magnetic field behavior is not reproduced by straightforward models of convecting ionic fluids. The wind structure does not emerge cleanly from standard atmospheric dynamics models. These discrepancies suggest our models are missing something about how Neptune really works internally. And since Neptune is the calibration point for sub-Neptune exoplanets, that missing something propagates into our interpretation of thousands of exoplanets detected by Kepler and TESS. The stakes of understanding Neptune are not limited to Neptune itself. They extend to our understanding of the most common type of planet in the galaxy. Let us now talk about one specific aspect of Neptune's atmosphere that is particularly mysterious: the fact that its methane abundance appears to vary with latitude in ways that are not fully understood. Methane in Neptune's atmosphere is not uniformly distributed. Observations in the infrared, where methane absorption provides a probe of the atmospheric chemistry, show that the equatorial region has higher methane abundances in the upper atmosphere than the polar regions. This latitudinal gradient is qualitatively similar to what is observed on Uranus, but quantitatively different. The distribution of methane reflects the atmospheric circulation patterns, where methane-rich gas rises from deeper layers and where drier, methane-depleted air descends. Mapping the methane abundance across Neptune's disk therefore provides indirect evidence about the large-scale circulation, which is rising and which is descending. The picture that emerges is of a global circulation pattern with upwelling at some latitudes and downwelling at others, broadly analogous to the Hadley cells that drive tropical circulation on Earth, but operating on a planetary scale and driven by different energy sources. But the details are not well constrained. The vertical structure of the methane distribution, how it varies with altitude, requires spectroscopic data at multiple wavelengths that probe different depths. Ground-based and Hubble spectroscopy has been used for this purpose, but the spatial and spectral resolution is limited. The variation in methane also has implications for the chemistry of Neptune's atmosphere and the formation of the clouds and hazes that create its visual appearance. Methane condenses at certain temperatures, forming methane ice clouds in the upper atmosphere. The distribution of these clouds, which are responsible for the bright features visible in Neptune images, is linked to the methane abundance and the temperature structure of the atmosphere. Understanding Neptune's methane distribution at the level needed to properly constrain circulation models requires spatially resolved spectroscopy that is beyond current Earth-based capabilities and would require an orbiting spacecraft with appropriate instrumentation. Let us talk about one more thing that is genuinely underappreciated about Neptune, about the fact that it was, very briefly, at the center of a controversy about whether a ninth planet exists in our solar system, and how this controversy connects to Neptune's role as the outer boundary guardian of the solar system. In 2016, Konstantin Batygin and Mike Brown, planetary scientists at Caltech, published a paper arguing that the orbits of a group of trans-Neptunian objects in the distant Kuiper belt and scattered disk were clustered in a way that was statistically unlikely to be coincidence. The clustering, they argued, could be explained by the gravitational influence of a large, undiscovered planet in the outer solar system, at hundreds of astronomical units from the Sun, far beyond Neptune. This proposed planet, Planet 9, was estimated to have a mass of approximately 5 to 10 Earth masses, several times the mass of Earth, but less than Neptune. A super-Earth, or mini-Neptune, in a highly elliptical orbit with a period of perhaps 10,000 to 20,000 years. The announcement generated enormous attention. The possibility of an undiscovered planet in our solar system, something with more mass than Earth that we had never detected, seemed remarkable. 6 years later, the situation is more complicated. The statistical argument for the clustering has been challenged. New trans-Neptunian objects have been discovered, and some researchers argue that when selection biases in the surveys are properly accounted for, the apparent clustering is not statistically significant. Other researchers maintain that the clustering is real and still requires explanation. No direct detection of Planet 9 has been achieved. Surveys with increasingly powerful telescopes, including the Vera Rubin Observatory, now coming online, have failed to find it in the regions where it was predicted to be brightest. This does not rule it out. Its orbit is so elliptical that it could currently be in a region of sky that is harder to survey, but the non-detection is constraining. The current status of Planet 9 is genuinely uncertain. It might exist. The statistical evidence for it has been challenged but not definitively refuted. The surveys have not found it, but have not conclusively excluded it. What is relevant about this story for Neptune is what it reveals about our knowledge of the outer solar system. If Planet 9 exists, an object several times Earth's mass at hundreds of astronomical units, we would not know it directly from current data. We would infer its existence from its gravitational influence on the orbits of smaller objects, just as Neptune itself was discovered. This is a reminder that the outer solar system is not fully mapped. Objects too faint, too slow-moving, too distant to have been detected in current surveys might exist in significant numbers. The Vera Rubin Observatory will survey the southern sky with unprecedented depth and cadence. It should either detect Planet 9 or significantly constrain its existence. But even Vera Rubin has limits. Beyond those limits, our knowledge fades rapidly. Neptune is the most distant planet we know well. Beyond it lies the Kuiper belt, the scattered disk, the inner Oort cloud, the hypothetical Planet 9. Regions we know poorly, and the true outer Oort cloud, regions we barely know at all. We are in the early stages of exploring our own solar system. Neptune is near the edge of what we have actually visited. Beyond it, largely unmapped territory. Let us now reflect on what all of this amounts to. Neptune is not peaceful. Its winds are the fastest of any planet in the solar system. Its storms appear and disappear on human timescales, with dynamics our models do not fully predict. Its internal heat source generates more energy than it receives from the Sun, by a mechanism we do not fully understand. Its magnetic field is tilted and offset from the center in ways our models of interior dynamics struggle to explain. Its moon, Triton, orbits backward, was captured from the Kuiper belt at enormous dynamical cost, destroyed Neptune's original moon system, and is now falling slowly inward toward its inevitable destruction in the Roche limit 3 billion years from now. Its rings are incomplete arcs, maintained by resonances with inner moons, slowly evolving and changing. It may rain diamonds in its interior, its clouds cast shadows, its jet streams blow backward relative to the planet's rotation. Its geysers erupt on the coldest large surface in the solar system, and we have visited it exactly once, for 12 hours, 35 years ago. The blue dot at the edge of our solar system that looks like a peaceful sapphire from Earth is one of the most violent, dynamic, and poorly understood worlds we know. It is a gravitational architect that shaped the outer solar system and may have driven the bombardment that preceded the rise of life on Earth. It holds a doomed moon that may harbour life in an ocean that will one day be torn apart. It represents the most common type of planet in the galaxy, in a region where our models are most uncertain. It is not peaceful. It is not remote in any sense that makes it irrelevant to us. It is a world we barely know, doing things we cannot fully explain, in conditions we cannot fully characterize, with a future already written in the slow mathematics of tidal mechanics. We have barely looked. Go outside tonight and look for Neptune.
You cannot see it with the naked eye. At magnitude 7.8, it sits just below the threshold of unaided human vision. You need binoculars at minimum, a modest telescope to resolve it as anything other than a star. Tonight it is in the constellation Pisces, a faint blue-white point indistinguishable from surrounding stars, unless you know precisely where to look and track its slow movement against the stellar background over nights and weeks. That faint point is 4.5 billion kilometers away. Light from the Sun takes 4 hours and 10 minutes to reach it. It is so distant that it completed its first full orbit since discovery in 1846, only in 2011, and it is nothing like what it appears. Here is what that faint point actually is. The fastest winds of any planet in the solar system, sustained at 2,100 kilometers per hour, more than 4 times the fastest tornado ever recorded on Earth, encircling the entire planet continuously, not as a storm event, as the normal state of the atmosphere. An internal heat source generating 2.6 times more energy than the planet receives from the Sun through a mechanism we do not fully understand. A magnetic field tilted 47 degrees from the rotation axis and offset enormously from the planet's center, generated not at the core, as planetary magnetic fields should be, but in the outer icy mantle, through processes our models do not completely capture. An interior where pressures reach millions of atmospheres, temperatures rise to thousands of degrees, and methane may break down to release carbon that crystallizes under extreme pressure and falls as diamond rain toward a liquid diamond ocean around a rocky core. A ring system of incomplete arcs, not full rings, but fragmented bands of material maintained by gravitational resonance with the inner moon Galatea, slowly dissipating, changing even in the decades since they were discovered by Voyager 2 in 1989. And Triton. A moon orbiting backward, retrograde, opposite to Neptune's rotation, because it was not formed here. It was captured from the Kuiper belt in the solar system's chaotic early history. It orbits in the wrong direction because it was never supposed to be here at all. The price of its capture was the destruction of Neptune's original moon system. Any moons Neptune formed with were scattered or consumed when Triton arrived. Triton is the coldest large surface we have measured anywhere in the solar system, minus 235 degrees Celsius, 38 degrees above absolute zero. And it erupts. Nitrogen geysers shoot 8 kilometers above the surface, driven by the dim sunlight, a 900th of what we receive at Earth, warming dark subsurface material enough to vaporize the nitrogen ice beneath. The geysers leave dark streaks blown across the plains of frozen nitrogen. And Triton is falling. Because it orbits backward, tidal forces drain energy from its orbit rather than add it. It is falling inward toward Neptune, slowly, imperceptibly on human timescales, but inexorably. In approximately 3.6 billion years, Triton will cross the Roche limit, the distance at which Neptune's tidal forces overpower the gravity holding Triton together. It will be torn apart. Its material will spread into a ring system larger than Saturn's current rings. Triton's destruction is not speculative. It is not a possibility. It is the inevitable mathematical consequence of its retrograde orbit, already underway, already written in the physics of its motion. It has been falling since the moment it was captured. All of this we know from one spacecraft, one flyby, 12 hours of close approach on August 25th, 1989. Everything we know about Neptune, every number cited, every phenomenon described, traces back primarily to those 12 hours, plus distant telescopic observations since. We have never orbited Neptune. We have never sent a probe into its atmosphere. We have never returned. Neptune is the most visited of the least visited places in our solar system. One visit, 35 years ago, 4 light hours away. The blue point that looks peaceful from Earth, that looks like nothing really, a star you need a telescope to see, is doing all of this right now. The winds are blowing at 2,100 kilometers per hour. The diamonds are falling in the deep interior. Triton is tracing its slow inward spiral. The geysers are erupting in the permanent cold at the edge of what sunlight can sustain. Right now. It will be doing this when you go to sleep tonight and when you wake up tomorrow. It has been doing this for 4.5 billion years. It will be doing this long after every mountain on Earth has been erased by erosion and rebuilt by tectonics. The outer solar system is not empty. It is not peaceful. It is not irrelevant to us. Neptune shaped the architecture of the solar system we live in. Its outward migration billions of years ago may have driven the bombardment that scarred the early Earth before life took hold. The same dynamical history that placed Neptune where it is, placed Earth where it is. We are connected to Neptune, not through proximity or any immediate physical influence, but through history, through the shared dynamical past of the solar system that made both worlds what they are. Find the binoculars. Look in the direction of Pisces. Find the faint blue point. Know what it actually is.